This is a video for AQA Mechanics, Circular Motion, Section 1.3, Motion in a Horizontal Circle. We know that from Newton's laws we have F equals ma, so it says that if an acceleration occurs, then there must be a resultant force. With circular motion, the acceleration we saw is towards the centre of the circle, centripetal, and therefore there must be a centripetal force producing that acceleration. So that centripetal force has got to come from somewhere. It can be such that if there was no force, then the body would continue in a straight line, and we saw that with a hammer thrower in a previous video, where the hammer continues going round in the circle if the athlete is holding it, but as soon as the athlete lets go, the hammer is going to fly off at a tangent. So because there's no longer a force producing the acceleration towards the centre of the circle. So tensions in cables, frictional forces, are all sometimes quite a combination of quite a few forces, but always producing a net force towards the centre of the circle to produce the acceleration. So we're now going to look at a few examples of these and where the forces might come from in particular cases. So in the first case we've got a particle to 0.2 kilograms, which is on the end of a light inextensible string, length 0.8 meters. Now light inextensible, that's a mathematical modelling sort of concept. Light means that we don't have to take any note of any mass that it might have, so it's so light that the mass can be ignored. Inextensible means it's not going to stretch at all with any forces. So both of these are approximations for the modelling. They can be ignored. The other end of the string is attached to a point at the on a smooth horizontal surface, so that's going to be the centre of the circle, and the particle is moving in a circle with angular speed of 2 radians per second. Now what we should do first of all is to try and draw a diagram of the situation showing all the forces that are acting. So here we are with the forces, and the acceleration is marked there with the double-headed arrow. So the acceleration we can put on as being equal to the thing that we want to find, so that we can then work out the force. The centre of the circle is over here somewhere, where this distance is 0.8 meters. So we've got the tension T producing that acceleration, the other two forces, the weight of the object mg and the normal reaction on the surface. We're told that the surface is smooth. Again, this is another modelling aspect. Smooth just means that there are going to be no frictional forces, or we can assume that the frictional forces are so small as to be ignored. Well, for circular motion then, we have that A is r omega squared, the formula we can use. So that is 0.8 multiplied by 2 squared, which gives us a value of 3.2, and that's meters per second squared. Newton's second law, acting towards the centre of the circle, tells us that F equals ma, and so therefore we can say that the tension T is the mass, which is 0.2 multiplied by the acceleration that we found, which is 3.2, and that gives us a value of T of 0.64 newtons. Well, this second example, then this is a bead on a wire. The wire is horizontal, so it's a diagram trying to represent that. The bead is threaded through or onto the wire, and so this time the weight and the normal reaction are again vertical but produced by forces on the wire, and there is a force towards the centre of the circle produced again by normal reaction at right angles to the tangent to the circle. So this is actually a very similar diagram to the last one. We've got the two vertical forces, weight and reaction, and then another normal reaction acting towards the centre of the circle, and that's the one which produces the acceleration. So here we have a bead which is on a dish, and there's a rim to the dish. So this time the acceleration is going to be produced by a normal reaction from that rim acting towards the centre. So the normal reaction from the rim is acting towards the centre of the circle in that sort of direction there. And if we look at a diagram of that, then we'll see it's actually very similar to the diagrams we've had before. This time we've got the edge of the dish on the right hand side of the bead, and then so therefore it's the normal reaction from that which is producing the acceleration. The other two forces, again the weight and the vertical normal reaction, are equal and opposite to each other. But again, we are making some assumptions. If you noticed on the video, the bead actually slowed down, so it wasn't a frictionless surface, and therefore the acceleration in that particular case wouldn't be towards the total acceleration wouldn't be towards the centre of the circle. However, if we assume that it was frictionless, then the acceleration is towards the centre. Here we have another situation where we've got a platform which is going to rotate. And you notice there the two different cases. On the first one, the coin stayed in a circle, but when we did it rather faster, then the coin flew off at a tangent. Now what's the reason for this? Well, in the first case, the frictional force is what was keeping the coin in the circle, but in the second case that frictional force wasn't great enough, so it couldn't keep the coin moving in the circle because the force wasn't sufficient to produce the acceleration towards the centre of the circle. But again, the diagrams look similar, and we have to think about the conditions though for the coin not to slip. So the frictional force is going to have a limit to it, which would then give us our maximum angular speed for the circular motion. So let's see if we can actually calculate that maximum angular speed for these particular conditions here. The coin, mass 4 grams, on a circular disc, distance 6 centimeters from the center of the rotation, and the maximum frictional force we can told is 0.08 newtons. So we want to find the maximum angular speed of the disc such that the coin doesn't slip. Well, we know for circular motion that the acceleration is equal to r omega squared. So we know r is 6 centimeters, so 0.06, and omega is the thing we're trying to find. So we've got 0.06 omega squared. Newton's law says that F is equal to ma, so that the frictional force then is equal to the mass, which is 0.004, multiplied by the acceleration, which is 0.06 omega squared. And we're told that that frictional force has a maximum of 0.08. So we can write that into our equation then. 0.004 multiplied by 0.06 omega squared is F, and that must be less than or equal to 0.08. And then that gives us a value of omega being less than or equal to 2.89 radians per second to 3 significant figures, or roughly 28 revolutions per minute. So this completes our video on horizontal circles, and indeed is the final video in the section on circular motion.